Hi, today's video lesson is going to be on chemical bonding. This is the second part. The first half we talked about ionic bonding, and in ionic bonding we found that the electron is transferred from one element to another, and as a result you're left with a positive charge and a negative charge which attract each other and create the ionic bond. In this video lesson we're going to talk more about the molecules and how covalent bonds are formed. Now in a covalent bond electrons aren't transferred but they're shared, so we're going to kind of talk a little bit more about what that means, and there's no positive or negative attraction force like we have here. There is going to be attraction forces we're going to see, but it's very different than we have for our ionic bonds. Okay, and then we're going to talk about how our covalent bonds can actually have what are called polar covalent. And what's going to happen is a net result of all of this is that we're going to go from this non-polar covalent gradually get more polar, more polar, more polar until it becomes ionic. And we're going to see that it's a gradual change from one to the other. So what we're seeing here is just an ionic bonding is a very dramatic version of covalent bonding. This is like the perfect system in the sense that the electrons are shared equally and completely. Here they're shared completely unequally, and that one atom completely has it. So our idea of bonding really is the same thing. It's the mutual attraction of electrons between two atoms. In this case, the electron is attracted to the chlorine more, here attracted to the chlorine and to the chlorine. So it's all the same thing. It's just looking at the two extreme cases of it. Okay, the extreme cases where the sharing is completely equal and where it's not equal. Alright, so let's going on. How is a covalent bond forming? Well, if we take a look at a hydrogen atom, if we just start with hydrogen, it has one proton, one electron. It has one proton and electron. We draw another one. These are those Lewis dot diagrams we're going to talk about in the next video. But you should remember this, right? This just represents the electron, represents the electron. Well, remember that hydrogens, both of them have a 1s orbital, so there's still room for an electron in that energy level. Okay, and it's still going, and it has an attraction because they both have a positive charge. So what happens is this hydrogen nucleus, the proton in the atom, is going to attract the electron from its own, right, because it's going to have that attraction force, and now it's going to attract the electron from the other hydrogen atom. So what's happening here is that that first hydrogen is going to have an attraction for this electron. So it's going to attempt to pull it into its energy level. Well, because this hydrogen pulls with equal force, it's going to also attempt to pull those two electrons, and they're going to both share those electrons. That's what we call a covalent bond. Okay, but what's going on here? What are all the energies and interactions that are happening inside these atoms? Well, if we take a look at the proton, it's going to be attracting the electron. So does this one. That's what these purple arrows represent, the attracting forces. Okay, which is going to draw the atoms together. Okay, so if we start down here, we have a hydrogen and a hydrogen. Now, here's what's called potential energy. Okay, this is a potential energy going up and potential energy going down. Going on the x-axis is what's called the internuclear distance. All that means is how far away our nuclei are, and that's going to give us what's called bond length. Okay, so if I start with the hydrogen atoms an infinite distance away, it's going to approach potential energy of 0. That there will be no potential energy in the system whatsoever. Now, as I take these two hydrogen atoms and I bring them closer together, what they're going to do is they're going to start attracting each other, and they're going to start to move closer and closer together. Okay, and what's going to happen is it's going to lose energy. Its potential energy is going to get used up as it starts to attract towards each other. Okay, why would that happen? Because the electrons are being attracted. So this electron is being pulled into this nucleus, and this electron is being pulled into this nucleus, and they're approaching and lowering the energy of those electrons. Because if its electron is by itself, it's got some potential energy moving around the nucleus. Well, if it's now between two, it's going to lower its potential energy because now it's being slowed down between two nuclei, and now it's going to be stuck in this area between the two nuclei. Again, can't say completely because we don't, Heisenberg's uncertainty principle, but it's a pretty good approximation. Now, as the atoms get closer and closer together, the distance between them obviously gets lower and the potential energy gets lower. All right. Now, why don't those atoms just keep coming closer and closer together? Well, because there's repulsion forces in there as well. Okay, so we've got repulsion forces between the two nuclei, right? The protons in both atoms are going to be repelling, and the electrons are going to start repelling. So they can't come completely close together. There has to be a distance between the two nuclei. Think about the hydrogen molecule right here. Okay, think about it as a coiled spring. Let's say we have a coiled spring. Okay. Alright, so it's not completely on top of itself. There's some space in between the coiled springs. And what I'm going to do is if I were to continue to push on these two ends of the coiled spring, right, the coiled spring is then going to come closer together. Okay, so I'm going to get the coiled spring. So if we think of the hydrogen atoms at the ends of each of those, at each end of the spring, there's a hydrogen here and the hydrogen here, and I push them closer together. Remember, this is at this point here that I'm looking at, taking these two hydrogens, squishing them together. Okay, they're going to come closer together, right, because I'm going to start causing those repulsion forces to be counteracted a little bit. And I let them go, all right, I remove the force of push, you know darn well that that spring is going to bounce back out. So if I were to apply pressure and make the internuclear distance even smaller and smaller and smaller, I'm adding tremendous amounts of potential energy to the system. Because if I let it go, they're going to start springing back out, and they're going to bounce back and come back down to this point. Okay? Now let's think of the opposite. Let's say that I take that same concept, that same idea of the coiled spring, but instead of pushing it together, let's say that I go in the other direction and I pull the spring apart. Right? I think you get the idea what's going to happen here. So if I pull the spring in the other direction, that would be making my internuclear distance greater. Right? I'd be pulling those atoms away from each other. Well, if I do that, you all hopefully know, let's change it to red just to be consistent here, that spring is going to get stretched out. Well, if the string is stretched out and I let it go, right, you get the idea that the spring is going to go back down. Boom, back to where it was. Same idea here. If I pull those atoms apart and I let them go, they're going to come back down here. Now, if I continue to pull on that spring, couldn't I at some point snap it and break it? And that's what we call breaking bonds, right? If we were to completely pull those two atoms away, we would snap the bond. We would say that they're an infinite distance away, and we remove, and that potential energy is now released. So that bond length that we are talking about is the length at which those atoms just constantly sit right there when they're not being acted upon. So if I'm not adding energy or pulling them apart, that's the distance, and that's why we have a covalent bond, because of the mutual sharing of those electrons between the two nuclei. All right. So what that leaves us with is molecules that can share electrons and create, this type of bond. Now, Linus Pauling discovered something called electronegativity. Saw that the atoms are going to pull with a different force. And we already talked about electronegativity in the last unit, and we know that it increases to the right and it increases up. Okay, so you should know that periodic trend, and you should be able to explain it using atomic structure. But for right now, if we're talking about why these molecules are doing what they're going to do, we need to make sure that we don't have to go all the way back to the atomic structure, I guess is what I'm trying to say. All right, so what I want to look at is if I look at two chlorine atoms together in what we call chlorine molecules, right? So the diatomics are going to share with an equal force, right? The electronegativity is the ability to pull the electrons in the bond. So therefore, chlorine would have a difference in electronegativity, right? If we look at electronegativity as En, right, we'll just abbreviate this En to make the notes a little bit faster. So we would just subtract 3.0 minus 3.0, we would get a 0. And that's the definition of a covalent bond, or a non-polar covalent bond, where the sharing is equal and there's no net charge buildup on either side. But if we look at hydrogen and chlorine, well, chlorine's way over here in the periodic table. Hydrogen is, over here. It's still not a metal, so it's not that low as the metals, but it's still pretty low. So my change in electronegativity would be the 3.0 minus 2.1, so I would get a difference of about 0.9. Okay, so therefore, now I have a polar bond. What this is telling me is that one of the atoms is pulling with a greater force. So therefore, the electrons are going to be attracted to this side more, and it's going to ruin the symmetry of my molecular substance, and I get what's called a dipole moment. All right, a dipole moment would be pointing toward our electronegative element. Okay, or we would put this partial charge, partial negative. So we get partial positive, partial negative. All right. Now don't worry too much about the calculations here. This change in electronegativity, you're not going to have to calculate that. You're never going to see that. I'm more concerned that you understand how to apply the periodic table. That if we're over here to the right, they're going to be higher at pulling electrons than the ones on the left side. Now, when we compare these two metals, by the way, just to continue with the notes here real fast here, if I were to take that chlorine again, and now I compare it with sodium, now I have a difference of 1, or I'm sorry, an electronegativity of 1 and a difference of 2. That is what we call ionic. Okay? Now, you got nonpolar, you got polar, and you've got ionic based on differences in electronegativities. Now, again, you're not going to have to worry about knowing the cutoffs on all these and what the numbers are. What you want to know is that if you have metals, they tend to have very low electronegativities compared to nonmetals. Therefore, they lose the electrons more and create a more dynamic difference between them, and you get a positive negative charge, hence ionic. When two nonmetals are together and they're not the same electronegativities, they're going to be considered polar bonds. Okay? And then if they're the two same atoms, then it's a nonpolar bond, and that's pretty much it. Now, what we're talking about here are bonds, by the way. These are just bonds. So we're not talking about molecules yet, we're just talking about bonds. So let me give you an example. If I were to take a look at water, H2O. Now you know that H2O is a hydrogen and 2 oxygens in the structure. Okay. If I compare that to CO2, then I need that oxygen on either side, and I get this. Now, if we look at the formulas themselves, it's still a 3-atom system, isn't it? There's 3 atoms in there, and there's 3 atoms in the carbon dioxide. So if I look at the bond polarities, just the bonds themselves between the oxygen and the hydrogen, oxygen is clearly better at pulling than the hydrogen is. So therefore, the electronegativity is going to cause a dipole moment to form here and to form here. Okay. Now the same thing is going to happen with carbon and oxygen, right? So we're going to have the oxygen pulls the electrons with a greater force, so therefore we get a pull here and here, and you get a difference in electronegativity. So we would say this is partially negative, and partially positive. Partially negative, partially positive, and partially positive. Okay. Now, when we're talking about bond polarity, that's fine, right? We're looking at the individual bonds and what make them up. But when we look at molecular polarity, that's when we look at the entire molecule. And the big difference here is that over here we're going to have what's called a polar molecule, and this would be a non-polar molecule. Okay, and the reason why has to do with the shape of this molecule versus the shape over here. Okay, and that's what we're going to get into in the next unit. The next topic we're going to start talking about is Lewis structures. Because I can split this in half due to its bent shape, I get a buildup of negativity on one side of the water molecule, and I get a positivity on the other side. And then over here, I don't have that. I have a linear structure, so therefore there's no way to really split this. Now this is going a little beyond what you need to know for right now, but that's where we're heading. So that's why we want to look at bond polarity versus molecular polarity. Okay, I think that's good enough for now. So I want you guys to take a look at the notes in the book and stuff, and I'll see you in class and we'll kind of go over it. Talk to you later.